Welcome to Formula 1 Maths. This is Mixed Exercise 9.01, GCE A-Level Applied Maths, Year 1. Mixed Exercise 9.01 is on constant acceleration. We've got 3 questions to answer. Question 1. A particle is traveling with velocity 20 meters per second. At a point A, the particle accelerates at a constant rate, reaching a velocity of k meters per second after 50 seconds. The particle then decelerates at a constant rate, coming to rest at a point after a further 30 seconds. A. Sketch a velocity time graph to illustrate the motion. Given that the distance between A and B is 1,540 meters, B. Find the value of k. So we'll start with our sketch. So this will be the velocity axis, and this will be the time axis. So let's put that in. So at the point A, when t is equal to 0, which is here, the particle is already traveling at 20 meters per second. So let's put that one in there. And then it accelerates to a velocity of k. So it accelerates, and the velocity will be k. And this acceleration is done in 50 seconds. So this time here is 50 seconds. It then decelerates from k meters per second to rest, where the velocity is 0 meters per second in 30 seconds. So we have this, and the time is 30 seconds. That makes the whole journey 80 seconds, because 30 seconds plus 50 seconds is equal to 80 seconds. For B, given that the distance between A and B is 1,540 meters, find the value of k. So the total distance traveled is equal to the area under the velocity time graph. So this will be given by the area under this velocity time graph. So I'm going to split the area under the velocity time graph into 2 sections. One for the motion during acceleration and one for the motion during deceleration. The one for acceleration is represented by the blue section, and the one for deceleration is represented by the green section. To find the area of the blue section, you're going to use the formula for the area of a trapezium, because the blue section, as you can see, is a trapezium. The formula for the area of a trapezium is given by half brackets A plus B times H. A, in this case, is 20 meters per second, and B, in this case, is k meters per second, because they are the parallel sides. And H, which will be the perpendicular distance between the 2 parallel sides, in this case, is 50 seconds. So for this area, we have half bracket 20 plus k times 50. For the green section, we're going to use the area of a right-angled triangle. And this is given by half times the base times the height, where, in this case, B is 30 seconds, and H is the height here, which is k meters per second. So if we add these two, you're going to get the total area, which will be equal to the distance between A and B, which in this case is 1,540. So we have this equation here. We can now reduce the fractions. 2 goes here 1, 2 goes to 25, 2 goes here 1, and 2 goes to 15. And this reduces to 25 brackets 20 plus k plus 15k equal to 1,540. Expanding will give us 500 plus 25k plus 15k equal to 1,540. Collecting like terms will give us 40k is equal to 1,540 minus 500. Reducing that will give us 40k is equal to 1,040. And solving for k will yield k equals to 26. So the value of k is 26. Question 2. A car moves along a straight horizontal road, starting from signpost A. The car decelerates uniformly at a rate of 0.8 meters per second squared, from a speed of 31 meters per second to a speed of 15 meters per second. The speed is then maintained for 510 meters. Finally, the car decelerates uniformly for 20 seconds before coming to rest at B. A. For the journey from A to B, find 1. The total time taken, and 2. The distance from A to B. B. Sketch the velocity time graph for the motion of the car, showing clearly the shape of the graph for each stage of the journey. So for A, we are going to consider the 3 stages of the motion. The first deceleration, the constant speed motion, and then the second deceleration. So for the first deceleration, we know that U is 31 meters per second, V is 50 meters per second, and A, acceleration, is minus 0.8 meters per second squared. It's negative because it is deceleration. So we've got U, we've got V, we've got A. We want T. So which of the Seward equations comes to mind? We're going to use equation 1. So if we put out equation 1 and do our substitution, we're going to get 15 equals 31 minus 0.8 T. Rearranging, you get 31 minus 15 over 0.8, and solving gives you 20 seconds. So for the first stage of the motion, it took 20 seconds. For the second stage, we are told that the velocity of 50 meters per second was maintained for 510 meters. So S is 510, U is 50 meters per second, and A is equal to 0. And A is 0 because it's a constant velocity. So when it's a constant velocity, it has no acceleration, and that's why A is 0. So we've got S, we've got U, we've got A, and we want T. So which of the Seward equations are we going to use? We can see that we're going to use equation 3. So let's put that one down and do our substitution. And we're going to get 510 for S, 15 for U, and then we've got our T, and the whole of this part, the whole of this term becomes 0 because A is 0. And so if we solve for T, we are going to get 34 seconds. And so the second stage, the constant velocity motion, took 34 seconds. Now the third stage, which is the second deceleration, we do not have to calculate any time at all because we have the time. We're told is 20 seconds. We can now add the various times to get the total time. So the total time is 20 plus 34 plus 20, which gives us 74 seconds. For the second part, we need to calculate the distance moved for all the 3 stages of the motion. So we need to calculate the distance moved in this stage, and that stage. So we start with the first deceleration. For the first deceleration, we know that U is 31 meters per second, V is 15 meters per second, and A is minus 0.8. We now want the distance. So we've got U, we've got V, we've got A, and we want S. Which of the Seward equations are we going to use? We are going to use equation 4. So let's put that one down and do our substitution. So 15 for V, 31 for U, and A will be minus 0.8, and that's where we have a negative sign here. And then we rearrange that to get this, and solving gives us 460 meters. So the car moved 460 meters for the first stage. For the second stage, we don't need to do any calculation because we are told that the velocity was maintained for 510 meters. Then we go on to the third stage. For the third stage, we know that the time is 20 seconds. Now, because the velocity was maintained in this second stage, it becomes the U for the third stage. And so U becomes 15 meters per second. And we also know that it comes to rest, finally, in the third stage. And so V is equal to 0. So we have T, we have U, and we have V. We are looking for S. So the silver equation that comes to mind will be equation 2 over here. And so let's put that one down. This, by the way, is the same as that. We can now do our substitution to get S equal to half bracket 15 plus 0 times 20. We can reduce the fraction. 2 goes a 1, 2 goes a 10, and that will give us 150 meters. And we are looking for the total distance from A to B, and this will be given by the sum of the various distances moved in the various stages. So we have 460 meters, 510 meters, and then 150 meters. Add them together, and you're going to get 1,120 meters. For B, it says sketch the velocity time graph for the motion of the car, showing clearly the shape of the graph for each stage of the journey. So we draw our axis, one for velocity and one for time. So we put that in, we get velocity here and time over here. First started with a speed of 31 meters per second. So we have 31 meters per second over here. And then decelerated to a speed of 50 meters per second. So we have that, and this will be 50 meters per second. And this, we know, occurred in 20 seconds. And that's what we got here. Then this speed of 50 meters per second was maintained for 34 seconds. And so if I add 34 to 20, I'll get 54. And finally, it decelerates from 15 meters per second to rest. And so we have this, and this occurred in 20 seconds. So if I add 20 seconds to that, the total time will be 74 seconds. And so this is the velocity time graph. Question 3. A ball is projected vertically upwards with speed 7√2 meters per second from a point which is 4.5 meters above the ground. Find A, the greatest height above A reached by the ball. B, the speed of the ball as it strikes the ground. C, the time between the instant when the ball is projected from A and the instant when the ball strikes the ground. For questions involving constant acceleration in the vertical direction, there are two methods that can be used to solve the question. There is the two-motion method, where one set of calculation is done for the upward motion and another set of calculation is done for the downward motion. There is also the one-motion method, where the motion is not split into two parts. I'm not a fan of the two-motion method because it's less accurate and is prone to mistakes. So for questions involving constant acceleration in the vertical direction, I'm going to use the one-motion method. So for this question, let's do a sketch to represent the situation. So this is the ground, and A, from where the ball was projected, is somewhere over here, and we are told that it is 4.5 meters above the ground. The path of the ball can be illustrated as follows. For A, we're looking for the greatest height reached above A, and this will be represented by the lowercase letter h. Velocity, acceleration, displacement are all vector quantities. So for the one-motion method, it's advisable to allocate or assign directions to the upward motion and to the downward motion. When the ball is projected from a point above the ground, it's advisable to regard upward direction to be positive and downward direction to be negative. So in all my calculation, positive direction will be upward, and downward direction will be negative. So for A, the ball is projected vertically upwards, and that means our initial velocity will be positive. Acceleration due to gravity is always acting downwards, so that will be negative 9.8 meters per second squared. We're looking for h, but at this point, at the greatest height rate, the ball comes to rest momentarily. So v equals to 0. So we have u, we have a, we have v, and we want h. So the silver equation we are going to use is equation 4. So let's write that one down and do our substitution. And we get 0 is equals to 7 root 2 all squared minus 2 times 9.8 times h, where h is replacing the s. If you simplify this, you get 9.6, h equals 98, and solving for h will give 5 meters. And so the greatest height reached above A is 5 meters. If you were asked to find the greatest height reached above the ground, then you will have to add the 5 meters to 4.5. But on this occasion, we are told to find the greatest height reached above A. B, the speed of the ball as it strikes the ground. With respect to the point from where the ball was projected, the ground has negative displacement, and so S will be minus 4.5. U is still 7 root 2 meters per second, and A is minus 9.8 meters per second squared. We're looking for V. The silver equation we're going to use is equation 4. Let's write it down and do our substitution. We get V squared is equals to 7 root 2 squared minus 2 times 9.8 times minus 4.5. Simplifying will give V squared is equals to 98 plus 88.2. Further simplification will give V squared is equals to 86.2. And then we find the square root to find V. And finally, we get V equals to 13.6 meters per second. And that's the speed with which it strikes the ground. C, the time between the instant when the ball is projected from A and the instant when the ball strikes the ground. Again, with respect to where the ball was projected from, the ground has negative displacement. So S is minus 4.5. U is still 7 root 2 meters per second. Acceleration due to gravity, A, is still minus 9.8 meters per second squared. We're looking for T now. So the silver equation we are going to use is equation 5. So if we write it down and do our substitution, you get minus 4.5 equal to 7 root 2t minus half times 9.8 t squared. Simplifying gives us minus 4.5 is equal to 7 root 2t minus 4.9 t squared. But we need to rearrange this so that the coefficient of the t squared becomes positive. So if we do that, we are going to get 4.9 t squared minus 7 root 2t minus 4.5 equals to 0. Now we've got a quadratic equation in t. So we go and use the formula to get the values of t. And the formula is t is equals to minus b plus or minus square root of b squared minus 4ac over 2a, where a is 4.9, b is minus 7 root 2, and c will be minus 4.5. So we obtain this equation here. If we simplify this, we are going to get t is equal to 7 root 2 plus or minus square root of 98 plus 88.2 over 9.8. And then solving will give us two values. One of them will be t equals to 2.4 seconds and minus 0.38 seconds, which is not valid. So the correct answer is t is equal to 2.4 seconds. And that's the time between the instant when the ball is projected and the instant when the ball strikes the ground. And this is the end of this set of questions in exercise 9.01.